Welcome to Pomodoro Joe for Sunday, September 17th, 2023. Today we're doing LeetCode problem 847, shortest path visiting all nodes. This is a hard problem. So we have an undirected connected graph of n nodes labeled from 0 to n minus 1. We are also given an array called graph, where graph at index I is a list of all the nodes connected to node I by an edge. So essentially this graph is a list of lists where the index is the node and the value is a list of all the nodes connected to that node. Return the length of the shortest path that visits every node. You may start and stop at any node. You may revisit nodes multiple times, and you may reuse edges. All right, so our example. So for this example, you might look at it and think, oh, well, it's 3, because you can just go from 0 to 1, 0 to 2, 0 to 3. There are 3 edges. But this is a single path. So if we go from 0 down to 1, we actually have to traverse back up to 0. So we have to go 0, 1, back to 0, to 2, back to 0, to 3, back to 0. So that'd be 1, 2, 3, 4, 5, 6 if we were to start at 0. Now in this example, they're showing us that if we start at 1, we can go 1, 2, 3, 4. So 4 is our shortest path. And it's interesting, if you look, we start at 1, but we could start at any of these. We could start at 2 and go 1, 2, 3, 4. Or we could start at 3 and go 1, 2, 3, 4. All right, our second example. We end at 3 and we start at 0. So we go 1, 2, 3, 4. Also 4. All right, and it looks like we have, very few nodes. That's interesting. That must mean that we can go through all the options. Good to know. All right, well, let's put 25 minutes on the Pomodoro timer and we will get started. So for this one, we'll have some result. We'll set it to infinite to start with because we're looking for the smallest or the shortest path. So we'll start with something really big and then we'll see if we can get something that's better. At the end, we'll return our result. All right, and I think for this one, I think my approach will be recursive, although there's probably a faster way to do this iteratively. But my thought here is if I know where it ends, like I can start or end at 3, I can just look back, well, how did I get to 3? What's the shortest path that ends at 3? So to find the shortest path that ends at 3, I can look at the connected node and say, well, what's the shortest path that ends at 2? And I can look at those connected nodes and say, well, what's the shortest path that ends at 4 or ends at 1? Whichever one of those has the better option, which will be 1. And then what's the shortest path that ends at 1? Okay, now I will also have to keep track of my state because as you notice, what's the shortest path that ends at 3? When I say, well, what's the shortest path that ends at 2? I have to know that that doesn't include 3. I'm already going to visit 3 in the future, so I need to keep track of what state I'm at. All right, so let's start with a recursive function here. Def shortest path length recurse. And this will take in the node. I'll just call it n. Well, no, I'll call it node. All right, so it'll take in the node, and if this node is the last node in my graph, then I can return 0. But how do I know if it's the last node in the graph? So that's where I have to pass in some state here. So let's see, I'll have remaining nodes. So my current node and my remaining nodes. All right, so if I don't have any more remaining nodes, so if not remaining nodes, then I can return 0. Right. Otherwise, I'll have to remove this node from my remaining nodes. So remaining nodes. Okay, now what is my remaining nodes? Right now I'm thinking of it as a set, so I'll have to remove. So I'll have to have some new remaining nodes if this is a set. So I'll have to make a copy of my remaining nodes, because I can't modify the input, because if I modify the input, it'll affect all the other recursive calls. So I have to make a copy, and then new remaining nodes. I'll remove this node. And in fact, I could remove this node before I make this base case call. So let's do that. Let's copy this, move it to the front. So we'll remove this node from the remaining nodes, then we'll check, do we have any more remaining nodes? If we don't, we're at the end, we can return 0. We made it. Otherwise, we have to go through every node that this node is connected to and find the shortest path that ends at that node. So for every next node in, and this will be our graph for this node, well, our option here is to make a recursive call. So we'll make one traversal, so it'll be 1 plus the shortest path length recurse on this next node, and we'll pass in the new remaining nodes as our state. Now our result will be whatever, oh, I don't have my result here. So then I have to have my result, and we'll set it to infinite to start with, and my result will be whatever is best, the current result or this new option. And at the end, we have to return our result. Cool. So I think this mostly handles our recursive call. Now there's one problem with this, and that is just toggling back and forth. Because right now, we can basically revisit the same node multiple times. So we could end up going from 0 to 1, and then back to 0, and then back to 1, and back to 0, and back to 1. We keep going back and forth. We're not actually checking our state to see if we've already seen this state before. So that's the next step here. We have to check to see if we've seen these remaining nodes and this node before. So our entire state is actually the node plus the remaining nodes. So we're at this node and we have these remaining nodes. That defines a state. Now, if we've seen this state before, then we don't want to do this processing again. So this sounds a lot like dynamic programming. So let's have some dynamic programming. So DP, we'll set it as an empty dictionary. And next, we'll need a key. So if the key is in this DP, so if the key is in DP, then we can return DP for this key. And the key is basically the state. Now I just mentioned the state was the node plus the remaining nodes. Now unfortunately, I made these remaining nodes a set, and that's not something I can hash to make part of my key. Oh man, so I might have to do something like, we could try this, but this is probably not a great idea. The key will be a tuple of our node and the string version of our remaining nodes. Now, I'm not 100% sure that the string version of the remaining nodes will always return the same string because the ordering might matter. So this might not work, but we'll give it a shot. All right, so we have a key that represents our state. That's this node plus the remaining nodes. And if we've seen this same state before, we can just return the value we calculated. Otherwise, every place we have a return, we'll have to set our value for this key. So DP for this key is 0. And down here, DP for this key is equal to our result. Okay, so now we've got our state. We're checking to see if we've seen it before. If we've seen it, we can just return the values. If we haven't seen it, then we have to go through and make this call. Now one thing, let's see, will this work? I think I need to set my key as soon as we get past this point. If we haven't seen this state before, I need to make sure that I record we've seen this state. And that I can do by setting my key to infinite to start with. And then hopefully we find a better answer here to replace that infinite. Otherwise, if we come back through here and we've seen this same key and it's still infinite, that means there's no path from this point forward that we can actually complete our entire graph, which should never happen. But anyway, we'll see. All right, so I think we've got our recursive function going. Next, we actually have to go through and start this whole thing off by checking every single one of our nodes as the potential start node. So for every node in range, let's see, I called it node in range n, and we don't actually have n. Interesting. So n is just the length of our graph. All right, so every node in range n, we'll call this. So let's see, this option is the shortest path length recurse for this node. And let's see, we need all the nodes for our remaining nodes. So let's actually have some set out here that's like all nodes. And that's going to be a set of range n. All right, we still have all the nodes to go through. And then our result will equal the best option, the minimal option of our current result, or this option. All right, wow, let's see if this works. Did I mean all nodes? I did mean all nodes. Thank you. Try that again. List object is not callable. Where am I calling a list? Right. For next node, graph index at this node. All right, try that again. Oh, right. So if we've already been to this node before, we've already removed it from our graph. So we can only remove it if it's still in the graph. So if node is in our remaining nodes, then we can remove it. All right. Wow, so many errors. Infinite not valid value. Oh, so I'm returning infinite here. Interesting. What's the test case? So maybe this isn't working, this set. All right, so what can we do that's not the set? Well, we could make this a string. We could just have remaining nodes be a string. And instead of just keeping track of which nodes by their actual name, we could use the position in the string to represent that node. So it's similar to the way this list has index represents the node. The position in our string could represent the node. So I could do something like that. Maybe I'll do that. So all nodes, instead of being a set for range n, we'll just have quote 1 for range n, or times n. That'll be all the nodes. Then here, we'll have to go, let's see. Instead of doing this copy, we don't need this copy anymore. We can just set the new node. So this is sort of like a bit mask. Actually, I could just use a bit mask. I'm doing this maybe more complicated than it needs to be. Let's go for a bit mask. Okay, I thought string might be easier, but it turns out bit mask is probably easier. Okay, so in that case, all nodes, let's see, I'm going to shift 1 by n, and then I'll subtract 1 to give me a bit mask that's all ones. And that's still passed in all nodes. Now my new remaining nodes, because I'm not using a set anymore, I can just modify the remaining nodes myself, and it doesn't matter. So that's remaining nodes. And I'll just do a bitwise AND with 1 shifted by node. And let's see, I want to flip that around, so I will do a not. So, all right. So now this will give me a bunch of ones where the node should be. It will now be a 0 because I flipped it around. And then I'll mask it with my remaining nodes. All right, so my remaining nodes will start out as a bunch of ones, like 1, 1, 1, 1, 1, binary. Bunch of ones. Then when we come in here, our remaining nodes then will remove our current node. So we essentially have a mask that's a bunch of ones, except there's a 0 where our node's place should be. We'll mask it with our remaining nodes. That gives us our new remaining nodes. So our current node is removed. Now let's see, this works well, and I don't have new remaining nodes, it's just remaining nodes. Check to see if the key is in RDPs, do this. If the new remaining nodes, okay, now this is just remaining nodes, and we can just check to see if it is 0. All right. Otherwise we go through, this is all the same, that's all the same, that's all the same, nothing else changes. All right, let's see if this works. New remaining nodes, right? I got rid of the new part because I'm just modifying remaining nodes myself. Okay, clearly I'm missing something. Okay, I have the length of my graph, I have all my nodes. I'll go through every node as the potential start. That's all good, this is all good, this is all good. And I'll return the result at the end. Oh, I spelled this wrong. Oh man, are you kidding me? We might have been passing this whole time. Ah, nuts. Let's submit to see how we do. We get a wrong answer. All right, let's use this test case and see what we did wrong. So one thing I can think of is we might want to do this after we do our DP check. So let's check our DP first. Then if we make it past this, then we'll do our remaining nodes. Then we'll break out, set this to infinite. All right, let's give this a try. There we go, that was the problem. All right, submit that, see how we do. And we pass. And let's see, we do terribly. We beat 20% for runtime and 15% for memory, so we don't do great. Let's see, can we do some things here? Well, we can do some minimums. Let's do this. We can do it here too. Same line, in fact, so let's just grab this whole thing. All right. Let's see. That gives us a tiny boost. Now we're at 23% for runtime, 15% for memory, so not great. All right, what else could we do? I mean, I'm so far off from getting like a 90%, I think I might just pass on this. I think recursive functions are generally going to be slower. There's probably an iterative way to do this that I'm just not gonna bother with because we only have 4 minutes left. But you can give it a shot. See if you can do this one iteratively. Maybe you can bump up this score to 90% plus. All right, well, I think that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.